first we needed to pick some parameters for our system. So we started with a beam waist of 0.45 millimeters, which we found in a previous lab. And we had a calculation for what we want the new beam waist to be to fill a 40 millimeter aperture, which is slightly smaller than what we actually have. And that gives us a 14 millimeter new beam waist, so a magnification of around 31. And we chose the objective to be a 9 millimeter focal length objective. So the second focal length of the collimator should be around 281 millimeters, and the closest one available to us was 300 millimeters. And then the optimal diameter of the pinhole in the spatial filter was calculated with this equation, objective focal length times wavelength over the beam waist, to be around 12.6 microns, and the closest one available to us was a 15 micron pinhole.
Alright, so here's the actual physical setup. We, as usual, aligned everything along the optical axis, and we have our cleaned up beam from the spatial filter. You can see there's only a tiny bit of higher frequency noise there, and you can really only see that in the dark. You can also see that it pretty much completely fills the lens aperture as we wanted it to. The lens, as before, is faced with the planar side this way to minimize spherical aberration, which we can see on the shear plate. If we had spherical aberration, we would have a much more cubic shape, but the fringes are basically straight lines, and we can also see that these straight lines are lined up with the zero line on the shear plate.
Okay, so now we're going to get the power of our high-power mirror. So the reason we got our first retroreflection is because we placed the mirror at the focal length of this lens, and the center of this lens looks planar, so that light will reflect back, collimated into the shear plate. The second retroreflection was when the radius of the wavefront of our beam, which is spherical, matches the radius of the wavefront of the spherical mirror, and again retroreflects back, collimated into our shear plate. Okay, so our first mirror location was at a focal point away from the reference lens, as you can see here, and that gave a retroreflection so that we could have our collimated light back into the shear plate and fringes aligned with the reference line. We then moved our mirror back a radius of curvature of the mirror away from where we were to again get a second retroreflection, and again fringes that were parallel to the reference line.
So for the low power mirror, we measured a couple of parameters. First with the mirror close back, and then second time moving them back, just measuring the same things and seeing how they changed. So our first measurement was the distance between fringes, which was a couple millimeters. This isn't really the right ruler to show that, but then we also took a protractor and measured the fringe angle with respect to this zero line, and then we measured the shear distance, which is the distance from the edge of the fringes to the edge of the beam here, and then we determined whether the fringes were going clockwise or counterclockwise, and by doing that with the mirror close and further back and finding how those parameters change with the distance we introduce here, we can calculate the radius of curvature. So we calculated the radius of the wavefronts for the low power mirror at two different positions of the low power mirror to be able to calculate the radius of the actual mirror and then compare our measurements. So we used this equation to calculate the wavefront radius, and then this equation with the wavefront radius to calculate the radius of the mirror, and these are the two values we got at the two different positions. They should be the same, but we'll notice that the wavefront radius equation is dependent on the fringe spacing, which at best we could probably measure to within 1 or 2 millimeters, and so propagating the error, since the values were only about 3 millimeters, that ends up putting this within our error bounds anyway, so this is sort of reasonable within our measurement error.
Next we tested a large focal length lens, placing it between the collimator and the shear plate, and we measured all the parameters on the shear plate again of shear distance, fringe spacing, fringe angle, and the fringes rotated clockwise, so we know this is a positive lens, and by calculating the radius of curvature of the wavefront at the shear plate, and adding that to the distance between the lens and the shear plate, we calculated a focal length of about 75 meters.